Hey everyone, welcome. Today we are diving deep into some seriously mind-bending physics. There's a new paper out that completely reimagines one of the most extreme objects in the universe. We're going to go beyond Einstein to take a look at a very special, quantum-charged black hole.
So this is the big question, right? What happens when you smash together the world of the very big, a black hole, with the bizarre rules of the very small? Quantum physics. Black holes are the ultimate cosmic battleground, where our best theories of the universe just, well, they fall apart.
You see, we have these two incredible rulebooks for the universe. On one side, there's Einstein's general relativity. It's our master guide to gravity, planets, stars, the whole cosmic dance. On the other side, you've got quantum field theory, which describes the weird fuzzy world of particles with stunning accuracy. The problem? These two rulebooks just don't play nice together, especially in a place as extreme as a black hole. So scientists are on this epic quest to build a bridge between these two worlds. They're searching for a more complete theory, one that can finally describe a black hole using the language of both gravity and quantum mechanics. And that leads us to the star of today's show, the Einstein-Euler-Heisenberg theory, or just EEH for short. The best way to think about it is like an upgrade to Einstein's classic equations. It's general relativity, but with some extra ingredients baked in from quantum electrodynamics, which is just our theory for how light and matter interact on the tiniest scale. Okay, so what's the big deal with this upgrade? Well, check this out. A standard black hole, the kind you learn about in school, is pretty simple. It's defined by just its mass and its electric charge. But this new EEH black hole, it's got a third property, a new ingredient that comes directly from those quantum effects, a unique magnetic charge, which the paper calls QM. This isn't just a tiny tweak, folks. This changes the fundamental nature of the black hole. All right, so we've added this new magnetic charge into the recipe. Let's see what happens. This new quantum ingredient starts to create some really strange, totally unexpected behaviors. And this is where things get, well, they get weird. So here it is, the first major bombshell from this research. As you crank up either the electric or the new magnetic charge on this black hole, its event horizon, the point of no return, it actually gets smaller. Now, your intuition might tell you that adding more energy should make the black hole bigger, right? Nope. Quantum physics flips that idea completely on its head.
And you don't have to take my word for it. The data is right here. Look at these graphs. Whether you're increasing the electric charge Q or that special magnetic charge QM, the result is exactly the same. The line goes down. The event horizon shrinks. It's a clear pattern. More charge, smaller black hole.
A smaller event horizon is fascinating, for sure. But what does that actually mean for a spaceship or a planet or anything else caught in this black hole's grip? Let's take a look at how these quantum charges mess with the orbits of both matter and light. First, we need to get our heads around a concept called the innermost stable circular orbit, or ISCO for short. I absolutely love this analogy. Think of a black hole's gravity well as a giant cosmic skate park bowl. The ISCO is the very, very edge of that bowl. You can orbit safely just outside it all day long, but if you get just an inch closer, you're spiraling in and there's no escape.
So what do our quantum charges do to this cosmic skate park? Well, something pretty wild happens. The data here shows that as you increase both the electric and magnetic charges, that safe zone, the ISCO, it gets pulled in closer and closer to the black hole. It's like these quantum effects are making the skate park bowl steeper, tighter, and a whole lot more dangerous.
Okay, so that's what happens to things with mass, like asteroids or planets. But what about particles of light? I mean, photons don't have mass, but their path is still bent by gravity. How do they handle this? And wouldn't you know it, we see the exact same pattern with light. There's something called a photon sphere. It's the region where light itself can actually orbit a black hole. And just like with matter, as the electric and magnetic charges on our EEH black hole go up, that photon sphere shrinks. Light can get much, much closer before it's inevitably captured.
Okay, so the charges shrink the black hole and they tighten the orbits. The final piece of the puzzle this paper looks at is how all this affects gravitational lensing, the way a black hole bends light. And they add a really cool twist. They account for the thin fog of plasma that actually fills deep space.
So the researchers set up two different tests. Scenario 1 was a simplified model. They imagined this cosmic fog of plasma was perfectly uniform, the same density and thickness everywhere. But Scenario 2 was much more realistic. They modeled a non-uniform plasma, where the fog is thicker closer to the black hole and thins out the farther you get.
And the result here is super important. The data is crystal clear. The simple, uniform plasma model predicts a much stronger light-bending effect than the more realistic, non-uniform one. So what does this tell us? It tells us that the environment around the black hole matters a lot. If we want to make accurate predictions, we absolutely have to account for the complex, messy reality of space.
All right, we've covered a ton of ground here. Smaller horizons, tighter orbits, complex light bending through cosmic fog. So let's zoom out and put it all together. Why does any of this theoretical work actually matter?
So here are the key things to take away. First, this EZH theory gives us a brand new way to think about black holes by adding in quantum electric and magnetic charges. Second, these charges aren't just some abstract idea. They have real physical consequences, actually shrinking the black hole and pulling in the orbits around it. And finally, and this is the most exciting part, all of these effects change how the black hole bends light. That gives us a potential fingerprint, a unique signature we could actually look for with our telescope.
And that leaves us with one final incredible thought. This research isn't just a fancy math problem, it's practically a treasure map for astronomers. It suggests that if we look carefully enough at the light from distant stars as it bends around black holes, we might just be able to spot the unique signature of these quantum effects. So, could we actually find a real-life quantum-charged black hole out there in the cosmos? The search is on.